The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to today's webinar. My name is Tracy Noble with ABB Power Systems, and I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items for you today. All participant audio will be muted during the event. If you would like to ask a question during the event, please use the question box on the GoToWebinar control panel. You should find that on the right side of your screen, and we will answer as many questions as we can throughout the event. Today's webinar is being recorded, and a link to the recording will be emailed to you following today's webinar. Please feel free to forward the link on to people you know would benefit from hearing this information. And a little message from our legal department. ABB is pleased to provide you with the technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose. And ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. Today's webinar, using IEC 61850 to solve protective relaying challenges, with Alejandro Schnikowski. And our presenter, Alejandro, graduated from Florida International University in Miami with a BS in electrical engineering. During his studies, he conducted research in the field of digital relays and centralization of protection functions within the substation, multi-object protection system. In 2002, Alejandro joined Bussier Communications, where he engineered, deployed, and tested Ethernet networks. In 2005, he joined ABB Inc., where he has contributed in a variety of roles from application engineering to management. Recently, Alejandro moved with his family to Raleigh, North Carolina, to take on his current role as Manager of Application and Support for Substation Automation Products in North America. It is my pleasure to introduce to you Alejandro Schnikowski. Enjoy today's webinar.
Okay, good afternoon, everybody, and thank you, Tracy, for such a warm introduction. The learning objectives for today. This is a webinar that builds up from our previous presentation on Introduction to IEC 61850, which was a presentation regarding some of the fundamentals and key aspects of the standard. You're more than welcome to go ahead and view that presentation, because some of the content from here, again, it will build up, and we are assuming that the audience has a base understanding of what the standard is, although I will make a brief introduction / review from last webinar. Today we're going to discuss essentially IEC 61850 with a focus on protection and control, and how IEC 61850, specifically Goose Messages, can help us solve some protection and control predicaments. So one of the things that we're going to first point, again, we're going to do a brief introduction / review of IEC 61850. We're going to discuss protection and control schemes and why information needs to be shared between devices to actually have functional schemes. We're going to discuss Goose Messages, though, in detail. We're going to discuss why exchange information via communications, what's the motivation for this technology to make it part of the IEC 61850 standard. We're going to discuss the anatomy or some of the details, inside details of a Goose message, so that you all have a better understanding from protocol stack perspective of what a Goose message is and what it is made of. We're going to discuss briefly the configuration process of a Goose message. What are the steps generally that are taken to configure a Goose? And this is something that we're going to be showing some screenshots from ABB tools, but this is pretty much very, very similar with tools from other manufacturers such as SCLG and Siemens. We're going to discuss how are Goose messages triggered and delivered. Very, very important question that I always get. We're going to discuss performance of Goose messages. How is this comparable to the speed and the reliability of an output contact, of a regular ice cube output contact? We'll discuss a few sample applications, and then a a topic that is of much interest, testing Goose messages. And this would be a very, very interesting topic, though. Very relevant for end users or system operators that are considering the deployment of Goose messages or are considering to digitize some input-output connections between IEDs. The idea of Goose messages presents opportunity, though, to develop new philosophies in regards to testing, and we'll touch on some of those points this afternoon. So again, thank you very much for your attention, and we'll go ahead and get started. So, as discussed in the previous webinar, though, this is an IEC 61850 based substation automation system. And what you will find, or what the assumption here, is that we have our primary apparatus, our substation breakers, and by utilizing a communications network, okay, the status points from the power system are being transmitted up to an HMI/gateway. And this bus right here, this line, it's really just a representation of a communications network in the form of an Ethernet network. So the key message here is that instead of needing to have hard wires between primary apparatus and a MMIC display and then an RTU, all of this information is being shared in the form of digital messages in 61850 protocols. There are really two. There are two sections of the standard, or actually three sections now of the standard that deal directly with communication protocols, and that is 61850 which defines the mapping of Goose messages as well as client-server as a protocol, though, to MMS and Ethernet. And then we have 61850-9-1 and 61850-9-2, which define protocols for the process bus, or the exchange of high-speed synchronous exchange of analog information from sensors over to protective relays. And the idea is that such analog, such signals, though, could be used for the execution of protection functions or metering functions. When looking at IEC 61850, it's very important to take into consideration. This is a very common question that we always receive. So, it's really hard to define what 61850 is. But one of the first starters is it's not a communications protocol. It's really, there's a combination. It's really a combination of points, combination of it addresses a combination of needs that at it, and with its introduction, though, the industry as a whole had. And one of them is the need for a standardized way to represent data and documenting it. So in the we're looking at protocols such as DMP or Modbus, Excel spreadsheets, or some sort of lists existed, though, that documented binary inputs, binary outputs, or registries with the actual meaning of that information. IEC 61850 addresses this point by providing the information as it is mapped in the protocol in a way whose syntax is easily understandable, and its naming convention is actually tied to functions and apparatus inside of the substation, and we'll discuss that in more detail in a couple more slides. But this is one key aspect of 61850, which is the data model. 6150 defines functions, defines data attributes that make up those functions, and it is all presented in a standard way. And since it's presented in a standard way, then that enables us to have common file structures to share and reuse this information. We also define basic equipment specification for the substation automation system. What this means is there's certain specifications though for the hardware that make up the substation automation system in regards to dielectric, in regards to SWC, search withstand capability, and so on. So there are some quality standards though associated with the equipment that it needs to meet in order for it to be part of an IEC 61850 system. The standard also defines performance requirements in regards to the speed and reliability of communication messages. This is something that's very important. So there's different classes of performance defined, and then depending of the type of message, though, the message should be delivered within that period of time. So in the case of protection and control applications utilizing Goose Messages, this is something that is quite relevant. So the standard defines that a Goose message should take X amount of time. Just how a manufacturer of an ice cube relay, which are typically found in output contacts of protective relays, though, can tell you what is the amount of time or what is the travel time of that particular output contact. So the standard, instead of leaving it up to the manufacturers to define that, standard defined it. And since all of these requirements are defined, then we can have tests that we can follow, and end users / consultants so can have the confidence that if a particular piece of equipment is tested or is deemed to be IEC 61850 compliant, it meets all of these different requirements. Another part that the standard defines, it's a protocol to report status information. What we're going to refer to in this presentation is ClientServer. And this is, and I'll just go back to the previous slide, this is the protocol that relays use to report their information up to an HMI/gateway. That's what we refer to as ClientServer. And this is a protocol that functionally or in principle, though somewhat similar to a DMP or a Modbus, where you have an ID, the ID is collecting information. That information is transferred over to a higher level system, though, or to a master in the form of a protocol. And in this case, IEC 61850 defines this ClientServer protocol as part of 8-1. We also define a protocol to exchange information between relays at high speeds, and this is Goose Messages, though, capability to exchange binary analog counter information, though, from one relay to the other in high-speed fashion. And then the last thing that the protocol defines in its edition 1 of the standards, protocol to distribute analog information for the purpose of running metering, protection, and control functions. This is referred to as the process bus, which recently the UCA released an implementation guideline, IEC 61859-2 Lite, which has enabled us manufacturers, though not only ABB, but other manufacturers, though, to actually make product implementation. So based on this concept of the process bus and digitizing current transformer and voltage transformer signals and publish them in an Ethernet network. So continuing on with our review of the first presentation, let's take a look at our data model, though, and what do I mean by that? Why is this so important? So when we look at this substation right here, there's going to be, or we can assume that there is equipment associated with each one of these breakers for monitoring purposes and for protection purposes and for metering purposes. So now let's just take the example of position of the breaker? Well, when you look at a protocol such as DMP or such as Modbus, the position of the breaker is really represented by those protocols as a binary input and status point. There's really no framework defined by DMP or by Modbus that particular binary input is the position of a breaker. And that's where integration comes into play, which is having to make that association of the power system or the actual application and the protocol, and then making use of that information. In IEC 61850, the information is presented with a naming convention that's directly tied to the application. And what I mean by that is, for example, logical information. In this particular case, we see this breaker, this incoming into this single bus substation. In the case of DMP, for example, this could be seen in the spreadsheet as device 5, binary input 4 for the A contact of that breaker, and then device 5, binary input 5 for the B contact of that device. The way this information is presented in 61850 is we define a logical node, which is, in this case, XCBR. It is a logical node, which it's the representation of a circuit breaker, then .POS, or position, and .STVal, which is the status value. So you could see if your substation grows and grows and grows, you're going to have a whole bunch of devices, different device numbers, different binary input numbers, but without having some sort of reference list that ties this protocol-based information to the application or the substation, you wouldn't really be able to know that that is the position of a breaker. Whereas in the case of IEC 61850, the way the position is presented is you have the ID name dot the logical node dot the particular data object and data attribute that's being presented. And this results in a protocol structure whose meaning is tied with the protocol definitions. Another example would be the 51P or the trip signal of phase time over current. In a DMP world, we'll have just binary input from one device, 6 and 7. In the case of IEC 61850, we have the name of the particular device, .PTOC, which is the logical node for a time delay over current function, .OP for operation, and .general, which is the status value, though, for the trip of that particular function. So as you can see, the information is presented in such a way that its representation is tied to the meaning or the application. And that makes integration much, much, much more straightforward. This naming convention also, and we'll keep this in mind, and I'll remind it throughout the presentation. This naming convention also now makes it much simpler to exchange information from one relay onto the other in digital form. And the reason for that is because if we were to look at a Goose message that's incoming to a particular device, you're not going to see binary input 5 or binary output 6 or bit number 7 that's either a 1 or a 0. No, you're going to see a digital value that has this particular name structure. So in the case of, let's say, a breaker fail function, you're not going to get a 1 or a 0. You're going to get this complete structure. So then at least you can understand that the signal that my device is receiving comes from a protection function. So from a documentation perspective and building protection schemes, this naming convention really facilitates that. And this is just a view of what I meant, or an expansion of what I meant by logical node and the actual data model of IEC 61850. 61850, we define a logical physical device. So in this particular case, this would be your relay. In the case of, we could just make some examples. This could be an REL 670, or this could be an SEL 421, for example. And then inside that physical device, we house what's called a logical device. And inside a logical device, you have different logical nodes. And what logical nodes represent, they actually represent functions. So let's say a 51, a 21, a 27, a 59. Well, there's a logical node for each one of those protection functions. For a 21, for example, though, there's PDIS, which is the logical node for an impedance element, though. For differential, you have PDIF. So all of these different protection functions, as well as monitoring functions such as metering or breaker control, there are logical nodes that are standardly defined in IEC 61 and 50. These are just some of the different logical nodes that exist, and it's important to see the first letter. Okay, really makes an association with the particular application. So P is protection, R is for related to protection. Some of the things that are related to protection are disturbance recorder, synchronizing functions, auto reclosing. In the case of C, you'll find a whole array of logical nodes related to control, switch controller, breaker controller, interlocking functions. In the case of M, we're looking at measurements. And there's a whole array of measurement functions, current, voltage, face-to-face, face-to-ground functions, and so on. So as you could see, when the standard was being written, thinking about the domain of a substation, what are the functions that are performed in a substation, and what's the equipment that's part of the substation. And there is a logical node for the most part for each one of these. There are logical nodes for HMIs. There's logical nodes for current, and there's logical nodes for transformers, for example. And this was the idea. I have a substation, okay? There are functions and equipment, okay? In this particular case, we have monitoring logical node. We have representation of switches. We have logical node representation of a breaker via XCBR. And then we have secondary protection functions such as protection time over current, protection distance, control interlocking, control of switches, and auto reclosing. And with multi-function microprocessor protection devices, the idea is that a single device could house all of these different functions. So if we just look back for a second and we see here this physical device, again, this physical device could be your SCL421 or your REL670. And then inside of it, there's going to be several of these boxes or several of these logical nodes which make up the functionality of the relay. And then inside each logical node or each function, there's data associated with it. So in the case of, for example, a metering function, you're going to have A for the amplitude though of phase A, phase B, okay, as a measurement of an analog quantity. In the case of this logical node, XCBR, for the representation of a circuit breaker. And then you're going to have data associated to that circuit breaker, health, pressure, position in this particular case we're showing. So it is a way, a standard way of representing all of these different functions, and that is first point that really makes the standard unique, which was not done with any other substation automation protocol prior to this. Second part that's very important to understand about the standard, though, just as a summary, is ClientServer, and this is now a protocol, again, that allows us to exchange information from our IEDs up to higher level systems such as an HMI, gateway, or a remote terminal unit. And what we do is, instead of, thanks to our naming convention, this allows us to perform our engineering in a much more expedited way. And the reason for this is because every IEC 61 and 50 enabled device is going to have its data model. Since it's standard and there's a language to document this information called SCL, or Substation Configuration Language, every manufacturer, every device from every manufacturer is going to have this mapping available in the form of either a CID or an ICD file. And the idea is that then you can grab that file, and then you will know what is the mapping or what are the functions, though, that are available inside that particular device. From a gateway or HMI engineering perspective, big part of engineering a system is programming the information that I'm going to fetch from the devices that are attached to the system. Well, in IEC 61850, populating that list is just as easy as drag and dropping that file, which, again, contains all the information that is enabled inside that particular device. And that's why this is so much more efficient to engineer. It's not a text file, it's not a Word file, it's not an Excel spreadsheet. It's a standard XML-based file that contains the capabilities or the template information of a device. Some of the other features, though, that are not contained in either DMP or Modbus, for example, are in ClientServer has a discoverable feature where you can have a IEC 61850 based client, and even without knowing what type of device it is, or even without knowing the SEL specific information of that particular device, you can go ahead and discover the data model. So you could actually connect to a relay or connect to a meter and read what is the available information from it, though, and make sense of it, though. You could browse the data model, though, of an IED, and then there's the reporting structure, which supports several triggering mechanisms, such as cyclic. You have buffer reports, you have unbuffer reports, and there's just a whole array of flexibility in regards to the reporting structure of IEC 61850 ClientServer. .61850 is the part where we are replacing what's done today via copper wires with digital Ethernet-based message. So what we're referring to in this webinar, though, as digitizing copper, which is accomplished, though, by Goose Messages or sample measure values. So Goose Messages, you can share binary signals in a high-speed fashion or analog signals in a high-speed fashion. This analog exchange is asynchronous, so it cannot really be used for protection functions, but the protocol allows you to send information other than digital information, let's put it that way. And then we have sample measure values in the process bus, which is actually a synchronous exchange of information of analog currents and voltages for the execution of protection or metering algorithms at the relay. So the idea of the process bus is, instead of having to hardwire current transformers and voltage transformers onto the back of the relays, we use the information from current transformers and voltage transformers is digitized by a device known as the merging unit, and the merging unit publishes the analog information in the network. And then any device that's connected to the network can subscribe to this. So that's also, it not only provides the cost savings of the reduced copper, but it now, since there's really no additional cost to subscribe to additional analog strings, you can have schemes where you can take in more analog information from more devices, though, to perform better protection schemes. So let me go ahead and check what we have on the questions pane so far. Okay, it seems like we have no questions so far. Good. Okay, so in that case, let's go ahead and discuss the need, our next topic of the presentation, which is the need to share information in protection and control. And without exception, protection and control schemes require information from the power systems and related apparatus. And this could either be in the form of current, voltage, but it could also be in the form of binary status signals, though, such is my breaker open, is my breaker closed, position of my load tap changer, position of grounding switches, position of disconnect switches. There's a whole array of information that about the power system that protection control equipment needs to know so that it can do its job properly. And the way that information is shared is in the form of cable connections, though, from those devices onto those devices or apparatus onto protection and control IEDs. And here are just some example applications. Interlocking schemes based on position of disconnects or grounding switches enable, disable the operation of other switches and or circuit breakers. This is one application. Position of breakers. It could also position of breakers or disconnects can also be used for enabling or disabling certain protection functions. Okay. Another case is adaptive relaying schemes. The use of position of breakers, load time changers to adapt relay operating characteristics. And what we mean by this is in the case of position of breakers is if you have a bus that's fed by 2 transformers and because of certain conditions one of the transformers is taken offline, that could considerably change the available fault current, though, for either ground faults or face-to-face faults. And on certain circumstances, that may merit, though, the change or the adaptation of the settings of some relays inside of the substation. So that information, that position or the topology of the substation is important to know to be able to make that decision. Another application where it is important to have an understanding of the topology of the substation is in bus differential relay schemes, where CT current switching may need to be performed internally by the bus differential relay to select the correct currents to add as part of the bus differential relay. Another example could be the position of the load tap changer in a transformer differential protection relay to normalize or to adjust the ampere turn balance calculation. As the load tap changer, with settings on a protection relay, on a transformer differential relay are based on the MVA rating, or the ampere turn balance settings are based on the MVA rating, and then the voltage level of winding 1, winding 2, or winding 3 in the case of a 3-winding transformer. CTE ratios are also part of that equation as well. But the key is that when a load tap changer is in place, that turns ratio relationship changes. And one way that is accounted for is by increasing or desensitizing the minimum pickup and slope settings of your transformer differential relay. One thing that can be done is to monitor the position of, or one thing that's done is to monitor the position of that load tap changer and adjust the ampere turn balance calculations or settings inside of the relay so that we do not need to desensitize the relay for that to have more sensitive protection. And then another reason where information needs to be exchanged between relays could be in reclosing, multi-breaker reclosing arrangements, so where devices need to choose based on pre-fault conditions which one is the breaker that's going to energize the line and which one is the one that's not going to energize the line. So for the most cases, if both breakers are closed and a trip occurs, there's always a predefined breaker that's the one that's going to energize the line. But if either of those breakers is open, refer to the fault or it's out of service, then there needs to be some indication, though, so that there's no further relays added to the reclosing or the re-energization of that line. And all of these require information from other devices. And then again, this information is exchanged via binary hardwired signals. Breaker fail, of course, that's another one. In addition to those applications, then we have functions that are strictly related to protection relays, though, such as to make protection more selective, secure, and dependable. In the case of communication-aided directional comparison schemes or line protection pilot schemes, we have an exchange of information from one terminal onto the other to determine whether the fault is inside the line or outside the line to enable high-speed clearing of faults during a whole array of conditions. Another function that depends on this exchange of binary information is breaker fail. Reclosing is another one, as just defined. If you have a reclosing relay and then you have protective relays that do not have the reclosing function built into it, then there needs to be an exchange of information between those protections, between those line protection relays and the reclosing relay to initiate reclosing, for example. And then you have blocking schemes where the pickup of one particular function will block the operation of another one. And this is, again, another case where binary signals need to be exchanged. And today, that's done with hardwire connections. So as we could see, just going through this array of conditions, though, wiring is an integral part of any protection control scheme. However, these connections consume time, effort, resources, and for the most part, standards are developed at the end user level to facilitate the reuse of this engineering, but sometimes that's not, sometimes that particular scheme, it's not going to fit on all of the stations, though, that require a breaker fail scheme. So we're looking at engineering, we're looking at material costs, copper, terminations, labor, labeling, testing of each connection point are all things that are just part of the deployment of these schemes, which in turn affect the time to deploy or the time to service of these stations. Reusability, as mentioned, it's a little bit of a challenge because of the fact that for the most part, once there will be variations from one installation on to the other. And then you have the challenge of large substations, where in the case of breaker fail challenges, in the case of breaker fail, there may be several connections from one device that's initiating breaker fail to the devices, though, on the breakers that need to be clear for that condition, and then all of the complexities and all of the testing that's associated with that. So the need to share information, how do Goose Messages address some of these issues? Well, one of the things is the engineering of these associations via Goose Messages is essentially reusable. It's all on the software. It's all in a software platform. It's essentially a digital, or it's essentially a digital connection from one device onto another. So as long as you're utilizing the same type of devices, the engineering can be pretty much reutilized. There's obviously will be changes from one station onto the other and from one application onto the other, but the engineering is essentially all in software. So it's much more easier to manipulate. The process of connecting one IED to another is self-documented in the substation configuration language tool. In essence, when you configure a Goose message in your system tool, as you're making this configuration, the software itself is documenting this association, what's going out from one device and what's coming into another device, essentially replacing logic diagrams, though, of IEDs inside of a substation. Deployment is accelerated by the fact that manual labor is minimized. All of these connections do not require any terminal strips that need to be wired into or any terminations that need to be landed. It's doing the engineering in your system tool and downloading the files onto the relay. Material costs are reduced because copper terminations, terminal blocks are eliminated or are reduced as part of a Goose-based protection and control scheme. And bigger systems can be engineered inside a single design platform from a protection and control perspective, thanks to the system tool and the ability for you to reuse blocks of engineering inside your system tool to replicate these types of connection. Okay, so actually I'm going to take a stop here, and I'm going to take some address some questions that we have in the question pane. Okay, so one question is, can I get a copy of the PowerPoint slides, please? You will get the PowerPoint presentation and a video recording of this presentation once the webinar is done. You'll get a link from GoToWebinar that you can access. CT and PT output goes to what device? To the IED, or is it digitized at the CT? That's a good question. The actual hardwired leads from current transformers and from your potential or voltage transformer go into what's called a merging unit, which is an electronics device that samples the analog waveforms and then publish that information in the form of a communications package. So yes, there is a device between the output of, there is a device between the leads of the CTs and the PTs and the actual relays, and that device is known as the merging unit. What is the acronym SLC? That is a typo. The acronym should be SCL, which stands for Substation Configuration Language. It is an XML-based language that allows, that's essentially an XML schema that documents logical nodes, functions, and connections between devices inside of a substation automation system. And let's see, please clarify the name of the device between the CT, PT, and the relay. Well, that is an MU, a merging unit. It's known as the merging unit. So just to reiterate that point, from your current transformers and your voltage transformers, you're going to have leads. Those leads are wired onto the merging unit, and the output and the merging unit will have a communications port that's connected to the Ethernet network that the other IEDs or protection relays are connected to, and then those relays can listen to the traffic generated by the merging unit. And by listening to that traffic, that essentially they'll be subscribing to the analog information from those current transformers and voltage transformers. In the current 9-2 LE implementation guidelines, that the makeup of that communication package is 4 voltages and 4 currents. So that would be phases A, B, and C, and your neutral for current, and then phases A, B, and C, and neutral for your voltages. Okay, let's go ahead and continue. So, what is a Goose message? Well, a Goose message is a generic object-oriented event. It's an Ethernet multicast message. It's fast and reliable distribution of information. And essentially, you can send status information, position of breakers, trips, pickups, alarms, just about anything, any type of information that you can associate with the output contact of your protective relay that you do today can be mapped to a Goose message or can be exchanged via Goose messages. Another type of information that can be exchanged are analog counters. That is also something that can be exchanged via Goose Messages. One of the questions that I always receive to what is the performance of a Goose message? Well, based on the IEC 61850 standard, type 1A, class P2, P3, messages should be received within 3 milliseconds. This is something that's quite comparable to ICE cubed relay output contacts, which are commonly found in protective, microprocessor protective relays from ABB, SEL, Siemens, GE, and all the major manufacturers. And those output contacts, they actually have a travel time of about anywhere between a quarter to a half a cycle. And the other time that needs to be accounted for, which I have a slide on that, is the debounce time of the device that's receiving that information. But we'll discuss that later on. This includes the transmission time to the other IED, similar to an output-input connection between two relays. So again, you're looking at about 3 milliseconds, and that is the specification of that's found in IEC 61850-6. Goose messages are sent based on change state, and we'll discuss what is the delivery mechanism and what triggers a Goose message and so on. But essentially, whenever a change of state occurs, Goose message is sent out to indicate that change state. So let's say in the case of breaker fail function, you're going to have the trip of a protective function connected to the breaker fail initiate input of another function or another device. Those would be connected. Whenever the device generates a trip signal, what that does is that generates or that triggers a Goose message that's going to represent the change of state from 0 to 1 to the breaker fail initiate timer. If the condition drops out before the breaker fail timer expires, a message changing state from 1 to 0 will be sent to the breaker fail relay in such a way that the breaker fail relay resets and there is no breaker fail trip. Second attribute of Goose messages is that they include diagnostic function or heartbeat to all devices subscribed, which is sent periodically. Goose messages are managed by Goose control blocks inside the relay, and this Goose control blocks is actually what's documented as part of your substation configuration language. So you can see Goose control block, and there are some addressing attributes that are important that we will see in a few slides. Goose messages do not send really individual, information. They send data sets or a collection of data. So we don't send individual data attributes. We send a database, and the way to view a data set is essentially a basket or a collection of or a bag that you can fill with different data attributes. Here's just one example. You could send one data attribute from one function. So here I have my data set. What the Goose message actually sends is this data set called protect. And then I can associate different entries to that particular data set. So you could send one Goose message with just one piece of information or one Goose message with several pieces of information. In this particular case, I have a data set with just one data entry, which is the trip data attribute of my PIOC or my protection instantaneous over current, PH for phase. I could have sent the phase segregated signals for phases A, B, and C, quality, and my timestamp. But in this particular case, I just decided to send general, which is the three-phase condition. Further, let's take just a look at some other attributes of a Goose message. Well, addressing. We have a multicast MAC address for the Goose message. And here I would like to spend a couple of minutes to really explain this. When we discuss MAC address, it is true that physical devices, protective relays, computers, anything essentially that has a hard Ethernet adapter has a unique MAC address that cannot be modified in most cases. Okay. So one of the questions that I received is, how come that we can actually freely allocate the MAC address for Goose Message? Well, the source MAC address, or the MAC address that when you look at the communications package, the source MAC address, who is sending the message, is going to be, the message is being sent by the relay, and that MAC address is unique because that MAC address comes from the Ethernet adapter, hardware Ethernet adapter of that particular IED. But the destination is what changes, and the destination is what is in the form of a multicast address, which in the case of the way a multicast works, ignoring any type of virtual LANs, is a message that goes out, and any port that's connected to, and any port associated to the switch where the relay is sending that multicast will have the capability to listen or to see that particular message. So if you have 24-port switch, for example, there's no virtual LANs configured, and you have a device that's sending a multicast message or a Goose message, you could connect your computer or the relay that's supposed to listen to that message to any of the ports, and the association will still be valid. Another criteria, you have application ID, and then you have application identifiers, and then you have the data set, which is the information that's being sent. So there's actually very, very few settings for this. You have your MAC address, which is your destination address. You have your application ID, which is just further filtering criteria. If you want to use virtual LANs, you can assign a VLAN ID. You can assign VLAN priorities. And then you have these two attributes, the min time and the max time, which I'll discuss in the anatomy of a Goose Message section of this presentation. Looking at the overall, looking now at the overall picture, what I have here is this particular relay, or my IED name A81J1Q01A1. I'm displaying the data set that's attached with my Goose control block GCB_A. And then as part of my system-wide engineering, I can actually see which devices are using that message as inputs. This is a very, very quick way to visualize who's sending what and who's receiving it. Something that on normal protection and control wire-based systems will require us to go through the prints or the logical diagrams or DC elementaries of each one of these devices. Here we get right away a visual of what this device is sending out, which is seen here in the data set entries. This particular case, this device is publishing the trip signal of the time over current function. And then we have these devices which are taking that as inputs, which are taking that information as inputs. If we now just look down at the specifics of the Ethernet network, we see that we have the following. First and foremost, here on top, we have the source and the destination MAC addresses for this particular Goose message. So on the source, we could see that the source address starts with 00. 00, that means that is the MAC address of a physical device, and it is indeed unique. Then this MAC address right here, it's actually a multicast, and we know that it's a multicast because the first octet is 01. And this is the destination address of our Goose message. And then if we just look at if we decode the traffic a little bit, we could see where the data set reference is, meaning what is the data set and what it is located as part of the SCL. We can see timestamp. We can see the state change number. We can see the sequence number. We can see whether the device is in test mode or not. We can see whether the device needs commissioning or not. And then we can actually see what is the information that's being shared in this particular case, which, as we see, this is actually a breaker fail function, RBRF, for related to protection breaker fail. And we have the trip signal, operation execute .general, and the quality. Here we just see, I just wanted to show a couple of data or pieces of information shared as part of a Goose message. In this particular case, I could see that this is, again, RBRF for my breaker fail function, OPEX.general, which is the actual trip or the operation. We see that the value is false, meaning that the function has not operated. And then there's something that's called the quality. And the quality actually is a series of numbers that indicate or that contain information about the device that's sending the information, that's publishing the Goose message. And in this particular case, this quality is indicating that the device that's sharing this info is in test mode, and we'll discuss that towards the end of the presentation as to why this is so significant. This is another example of information to share, which is the breaker or the position of the breaker. And in this particular case, we could see XCBR, or the physical representation of circuit breaker instance number 3, position, the quality. Quality is good, meaning that this device is not in test mode. And then we could see the position. Position is actually a 2 bits. It's what's called a DPS double point status, so it could be 11, 01, 10, or 00. In this case, the device is reporting a position of 01, meaning that the device is open or it's in the off position. And then we have the same, but for XCBR number 4, which is just another breaker that this relay is reporting the information to. Okay, so let's go ahead. I have a few questions here. How can we reach time of 3 milliseconds? Well, this is the time, this is the amount of time that it takes the device to compile the Goose message and then send it over the network. So if let's say, you know, if there's obviously a network transmission time, for all practical purposes, if the information is being exchanged inside of a substation where the physical distance is, it's pretty much negligible given the transmission speed of such messages, then you're going to be very, very close, less, you're going to be at 3 milliseconds or less for sure. So that is, you know, speed is really a measure of bandwidth and distance that the message has to travel. And IEC 61850 defines 100 Mbps or above network speed. So that is not a problem for it to be achieved. I have a question. Can a relay act as a merging unit? The answer is no. Okay, and then here we have, let's see, then I have a question. Please help further explain the multicast MAC address. Are they being processed at Ethernet switch or individual relays? How to implement multicast instead of broadcast? Well, the information on when the destination MAC address, okay, at 01, it's going to be, it could be processed by the switches if virtual LANs are assigned. Otherwise, the multicast could essentially behave as a broadcast, okay? So the difference being that, you know, it could go like, let's say that you have a 24-port switch, and let's now say that you have 12 ports assigned to one virtual LAN, and then you have the second, ports 1 through 12 are assigned to one virtual LAN, and then points 13 to 24 are assigned to another virtual LAN. If the message goes out, if the Goose multicast goes out with a particular virtual LAN ID, then that message is either going to be forwarded to ports 1 through 12 or ports 13 to 24. In that case, the behavior is not a broadcast, but again, there's some specific ports where the information is being forwarded to. In the case where no virtual LANs are being assigned and you send the multicast, then that message is you're going to have the capability of listening to that message at all 24 ports of that switch. So I hope that helps clarify that. Okay, now let's just discuss real quick how to configure a message. And every message starts with some sort of SCL or substation configuration language file. You have SCD, which is a file that contains the complete configuration of the substation, all the relays that are part of your substation automation system, all the Goose messages that are being sent out, and then to which device are those messages going in the form of inputs. So again, your substation configuration description presents a piece of information that documents the input-output relationship between relays. And this is something, again, pretty invaluable that today with cable connections will require us to go through prints, essentially. To start or to get to that substation configuration description, we have to start at one point, and we need to start with the individual files from each relay. And those files could be in the form of an ICD, which is an ID capabilities description. That's a file which is also referred to as a template file, which is a file that just contains the logical nodes or the data model structure of the device without any Goose message or report control block configuration. In the case of a CID, the CID is essentially the same thing as an ICD, a description of the data model of the relay, but on top of this, we will provide any Goose control blocks that are being sent, any inputs onto the relay, and any report control blocks. And the idea is that you start here in the bottom left-hand corner with all the ICD or CID files from your relays from different manufacturers. You take that information into a system tool. You publish, and you publish your Goose messages. You assign those Goose messages as inputs to devices inside your substation. The output of that process is an SCD file or your substation configuration description, and then that file is taken to the relays, and that file is downloaded to the relays using the individual tool from each manufacturer. In the case of ABB, it's PCM600. In the case of SCL, it would be Architect. In the case of GE, it would be Enervista. In the case of Siemens, Dixie. But the key is this process down to this point can be all accomplished in one single tool. And the outcome of this, again, is a single electronic file that documents all of these input-output connections. So when we look at the configuration of a Goose message, we could have, depending on the software that's being used, you could have a view of your substation, which essentially gives you a representation of your individual relay and its connection to the system, substation, voltage level, and then the particular bay where this particular relay is associated with. Then you could also have a view of just all the relays that are connected to, that are part of the project. And then you also have something that's called the communications section. You can have one or you could have multiple communication networks. And the communication section actually describes which device or which ID is connected to which network. If you have time servers, if you have HMIs, all of this is documented inside this. So IP addresses, all of that is documented, ID names and IP addresses and so on. It's all part of this file structure. First step to create a Goose message is to create a data set and populate that data set. So here I'm selecting a particular relay, AA1, B1, QO1, A2. It's a good idea to select names that really identify the relay within the system. So AA1 would be for that substation, B1 representation of voltage level inside that substation, QO1 for the first bay inside that voltage level, and then A2 for the second ID that's part of that bay inside that voltage level inside that substation. So by just looking at the name, I can identify where that relay is and what it is associated with, instead of just saying REL 670, which, you know, okay, it's a line distance relay, but to which line is it tied to? Next step is, again, we create a data set. In this particular case, we're creating a data set called protect. And then the last step to create the data set is to populate or to add the data attributes that I want. In this particular case, I'm adding the PPTRC, or my general trip function. There's 3 instances. I'm adding the 3-phase trip and the quality for each one of those. The next step is I need to create my Goose control block, or the Goose control block that this relay is going to use to publish or to send this information. And I'm creating it here. I define my different parameters, tmin, tmax, define that this is a Goose, define the destination MAC address, and application ID, virtual LAN, and VLAN priority as adequate. Last but not least, I need to connect this Goose message or this outputs to other relay inputs. And in this particular case, this is done in this particular piece of software, this is done in a matrix view, where all I have to do is select the relay and then put an X or tie it in a matrix form. Now, this is one part that's very, very, very important to understand. When we do a Goose message, it's essentially the same thing as wiring an output contact and then wiring it to the physical input of a relay. Now, what that particular device that's receiving that information does, it's something that's still that's really something that's not within the scope of what a Goose message is. Goose message is just a mechanism to share that bit of information. Now, how that information is tied, and if it's tied to a breaker fill function or if it's tied to the trip function, it's something that's now up to the software of each individual relay. In this particular case, this is just a view of PCM 600 where I'm showing that I am receiving this information. I'm receiving the position of breaker 1, I'm receiving position of breaker 2, and then I associate that with different elements within my configuration. And this is now, again, this is not within the scope of 6150. This is now within the scope of each individual relay as to how the relay will use that piece of information. So this could be SEL accelerator, and how do you use that, bit to affect logic inside of your relay. This could be EnterVista as to, again, how do you use that bit as a piece of information to affect your logic inside of the relay. That's all we're doing here. This is just the way it's represented inside PCM 600, so that there is an understanding that, hey, that piece of information is coming from this device. Oh, and by the way, it is pretty straightforward to see that this is a breaker fail trip function. It's pretty straightforward to determine here that, oh, this is the position of this breaker, and oh, this is the position of this breaker. And I can understand that because of the logical node naming convention, RBRF, in this case CSWI for controller of circuit breaker, and then I could see that they're sending POS or POS. Now, trigger mechanism of Goose Messages. Goose Messages are triggered by the following events. Periodic, which means that we send a heartbeat message to make sure that the connection, okay, between the device that's supposed to send and the device that's supposed to receive this information it's in good standing. So the period of this message is defined by Tmax in your Goose control block. In this case, this is sent to 10,000 milliseconds or 10 seconds. So every 10 seconds, the devices that were here connected to that message will expect a message from the device that's publishing this information. If they do not receive it after 10 seconds, then they can trigger an alarm and they can inform that the connection is broken. And that's what I meant, and this is the mechanism that allows Goose Messages to be self-monitoring connections. The second delivery mechanism, which is more interesting, is based on the change of state of the data. So in this particular case, we could see how the information change, the information containing this Goose message, which is for breaker fail, the operation of a breaker fail element, change from 0 to 1 at this particular time. So whenever it changed state, we send a Goose message. Looking a little bit deeper into this, one of the questions that always comes up, well, how come, if everybody sends information at the same time? Well, Goose message reliability is based on repetition. So whenever a change of state occurs, we actually send 5 messages for that containing that same change of state. As you can see here, that those they are spaced out sequentially, and you could see here in the presentation this dot, this darker dot, it means that the change of state occur. This is another time that we send the message. This is another time we send the message, and then this is another time that we send the message. So we are building reliability by repetition. Now, going back to these periodic messages, though, I mean, they can be used to monitor the connection between IEDs. When devices expecting a periodic message do not receive it on time, they provide an alarm to inform that the connection has been broken. This effectively makes the I/O connection self-monitoring and alarming upon failure. So when we take a look at this piece of switchgear that obviously have multiple dozens of connections, how is this done here? How is this self-monitoring in this particular case? Well, the way this is monitored is every 5 years, every 3 years, so depending on the end user's schedule, somebody's going to have to check all of these different I/O points. And whenever a problem occurs, it's going to be found in one of 2 ways. Either the scheme does not operate correctly because that particular connection altered the way the scheme should have behaved, or the problem is found during routinary testing. But there's nothing that can be done between those 2 events to really diagnose that a connection has been broken. Goose Messages, based on your Tmax, you're going to get an indication that that particular connection has been lost. Operators can be alerted based on this, and corrective action can be deployed immediately. Goose Message performance. As we discussed, it's something that's very, very comparable to hardwired output contacts, and the math is pretty simple. The output contact travel time is anywhere between quarter of a cycle to half a cycle, and I emphasize again, these are not solid-state output contacts that I'm assuming, but these are ice cube relays, which is what most protection relays utilize. So just the travel time of that output is anywhere between a quarter to half a cycle. Now, substations are a harsh, noisy environment. So to avoid the inadvertent assertion of physical inputs due to induced voltages, due to transients on devices, protective relays have debounce time or filtering times. And that filtering time is usually around a quarter of a cycle. So the total amount of time that it will take one device to realize that that information, that input has actually become a 1 and act upon it is anywhere between half a cycle to 3/4 of a cycle. In the case of a Goose message, this is something that is around 3 milliseconds. So as you can see, there's some performance gains utilizing Goose messages on that front. Since Goose messages are properly structured Ethernet packages that have checksums associated with them, there are no transient concerns at that point. There's no way that a transient could modify the Ethernet packet and then in turn be wrongly interpreted by a receiving device, since there are checksums that protect devices from that. Now, some sample applications, we've mentioned that throughout the presentation, but essentially anything that requires the exchange of information from one relay onto the other, which today is done via hardwired connection. So breaker fail could be one candidate, digital fault recorder signals to initiate a DFR, another candidate, transfer schemes, which require, again, significant amount of hard wiring from one device onto another, could be a candidate to apply Goose messages. Reclosing in multi-breaker arrangements where the reclosing function is outside the line protection relay. Interlocking and devices to monitor the position of the load tap changer, and again, just about anything that you can think of that shares where information is being shared from one device onto another. And that takes us to final topic of our presentation today, which is testing Goose messages. So testing for end users today, it's a familiar challenge. However, with the testing itself it's quite familiar, but how to test in a Goose message-based system, now you have unfamiliar equipment and unfamiliar technology. And one of the questions that I often receive is, where is the physical isolation? Where is the physical barrier? Since now Goose message is not something, it's not something that's tangible from a field engineering perspective. There's no way you can break that connection other than pulling the network cables out. And even then, there's really no way, no direct feedback that you can determine what is the value of the variables that are being sent by that particular device upon reconnection to the network. So today, with hardwired connections, we use test switches to isolate the relay, to block relay outputs from operating coils, whether are trip coils, closed coils, or physical inputs from other devices. So how is that done? One of the key requirements is that the testing of Goose messages needs to replicate the behavior of testing with hardwired equipment. Outputs needs to be isolated. In our particular case, this means that the outgoing Goose messages need to be, the outgoing Goose messages from devices that are being tested need to be blocked, need to be supervised somehow. Somehow we need to tell the system that somehow those messages need to be blocked. But at the same time, those messages should allow for devices to perform the testing. And then the second requirement is that there needs to be visual indication that the device is being tested so that the blocks can be removed to resume normal operation. And here I have a picture though of a a test switch that we use to, block trip and close circuits. And, again, by using this, you're still allowed to measure the operation of the output contacts of your relay to be able to perform your testing. And let's say if you're doing a reach test, or if you're doing a timing test, you can still monitor the output contact of your relay. And at the same time, you have pretty solid indication here that the device is being tested, so that this provides visual indication to field engineering that if the device is to resume normal operation, this needs to be removed. So how do we accomplish those two things with Goose Messages? Well, one of the key aspects that when the standard was being defined was the need to have some sort of mechanism, or the need to have mechanism to indicate that a device is on test mode. And the way this information is shared is via the quality. So when we look at the quality of a device, okay, that's part of the data set that's being transmitted, we could see whether the device is in test mode or not. And in turn, the device that's being tested should change its quality from good to test in such a way that every device that's using this Goose message should be able to identify that this device is being tested, and in turn should not react to that information if that is the desired behavior. So the key here is quality should be transmitted as part of the Goose message, and then the quality flag should be used to adjust the behavior of the devices that are subscribed to that particular message, so that they recognize that their peer is being tested. So how does this work? Well, quality is used by the subscribed relays to validate the incoming message. When a device is put in test mode, the quality is of its published data will change from good to test. Subscribed devices recognize this and block the inputs from the device in test mode. By blocking the inputs from the device in test mode, we mean just that, equivalent to opening up the finger of a test switch. The association is broken and will resume once the quality changes. In the case of ABB relays, we provide visual indication in the HMI that a particular device is in test mode, so that once testing is completed, there is visual indication that that device needs to be taken out of test mode so that normal operation of the system can resume. And just getting down into a little bit of the nitty-gritty details, in our case, in the case of the Reliant relays, the receiving block can actually provide 4 types of information. The first one is the actual status of the binary point that's being sent, whether it's a 1 or a 0. Then we can say whether the data is valid or not. Then we could say whether the communication is valid or not. And then we can actually also indicate whether the message that's being received is in test mode or not. And then these variables can in turn be used internally in the relay for different purposes, though. But the key is this: quality has to be used to indicate that a particular device is being tested, and it is exactly the equivalent to somebody going to a panel, pulling off the test fingers, and that essentially isolates the outputs of that device that's being tested from the inputs of other devices that are still in service. Outside this philosophy, we also have to take into consideration that new set of tools are needed. How do we monitor these Goose messages? And the good news is that most major relay tested manufacturers support Goose messages. Omicron, Megger, Doble, they all offer test sets and software that can monitor these devices and stop and measure, and measure that the devices or that the relays have operated just the same way as they would when an output contact closes and they either monitor potential or continuity. Now, how do you get an understanding of the system, though, when a test set is not available? How do you measure continuity on a Goose message? Well, the way that's done is by using troubleshooting tools or DAGMA's IEC 61850 testing tools. There are few available that can provide field engineering with immediate feedback as to what is the value of certain conditions. In this case, I'm showing what is the value of my breaker fail function. We could see that I am looking at this device, circuit breaker fail function operation, and then I could see whether that is on or off, and then I could see whether it is that particular function is in test mode on or not, which in this particular case it is. We can also see, and we can also get a visual on when those outputs or when those Goose messages change state with a timestamp with this particular tool. So this is also something where the darker dots actually indicate when a Goose message was sent, and then I can just scroll on my timing bar to get an understanding of the time at which that particular message was sent so that we can gauge performance this way. So, in conclusion, Goose messages can help protection control engineers deploy schemes faster while reducing material and labor costs. Goose message engineering can be reused with ease thanks to substation with substation configuration language and system tool approach. Goose messages are documented during the configuration process in SEL. Use system tool approach to achieve this at a system level. Connections via Goose messages are monitored and triggered and alarm when broken. Testing equipment and philosophies are in place to test Goose messages, and this can obviously be adapted and developed based on the particular requirements of the system operator. And with that, I'm going to go ahead and address a few questions that I have here. Okay. I have a question here. Can 6150 handle teleprotection such as a line differential scheme? The answer is no. IEC 61850 90-1 actually defines schemes to share binary information from one terminal to another, from one substation onto the other, but this is not the info. This is more for directional comparison, communication-aided directional comparison pilot schemes. So blocking schemes or POTT or PUTT schemes where you're just sending the binary information to indicate whether the fault is in the line or outside the line that's being protected. But yes, you can use Goose messages for that purpose. How do you use the heartbeat alarm in the relay logic? Is it a separate data attribute? No, it's not a data attribute. A data attribute is the information. Data attribute is the information that's contained in your data set or the information that you're sharing. The heartbeat is just the mechanism of there's one device that's sending the information. There's one device that's expecting that information. If I don't receive that information periodically per the TMAC setting, I assume that something happened with either the connection between the two devices or with the other device. At that point, this is something that varies from manufacturer to manufacturer, but both of them provide bits or variables available that can then in turn trigger, change of state on client server. They can then, close an output contact to go to annunciator, or there's many other things that can be done. In the case of ABB relays, that information can be used to send a report to the substation gateway or to the HMI to inform that this disconnection has occurred. There's a question here. Do you have a communication tool that allows you to monitor the traffic between all relays in IEC 61850 network? From an ABB perspective, yes, that is correct. There is a tool called ITT 600, which allows you to monitor both Goose as well as MMS traffic. I'm just going through the questions, so that's why you guys are here in the silence. Okay, so I guess the last question here, just to reiterate the question about pilot schemes, you can by using Goose Messages, you can exchange information from one terminal to another terminal, and again, with this information, you can implement unblocking schemes. And then you can also implement permissive schemes. Okay. However, you cannot use Goose Messages to do a line differential scheme, where a line differential scheme, you are exchanging samples of data from one terminal on to the other. And each relay at each terminal, it's making an evaluation of the local samples versus the remote received samples, and then making a delta or a subtraction between those two quantities, and then determine what is the current that's coming into the line versus what's the current that's coming out of the line. You cannot do that with Goose Messages. However, sending the bits for an unblocking or a permissive pilot schemes, that is something that you can do. And with that, we'll end today's session. And this webinar is brought to you by the Reliant product family, next generation of protection and control IEDs from ABB. Reliant, the perfect choice for every application. Widest range of products for power systems protection, control, measurement, and supervision. Interoperable and future-proof solutions designed to implement the core values of the IEC 61850 standard. ABB's leading-edge technology, global application knowledge, and experienced support network ensures complete confidence that your system performs reliably in any situation. Thank you very much, and we'll see you on our next session. Thank you, and have a great afternoon.